Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 1st, 2025, about a week ago. It shows how we can create best-in-class encoder models for a fraction of the usual computational cost by adapting existing LLMs. The paper is titled, "Should We Still Pre-Train Encoders with Masked Language Modeling?" And the implications for how we train powerful text encoders are pretty significant. The authors ran a huge controlled experiment to compare two major pre-training methods, finding that each has unique strengths. Also, the authors shared their implementation on GitHub, and it's quite comprehensive. You'll find their Optimus training library, which is a flexible framework for training models efficiently on different hardware, whether it's CPU, AMD, or NVIDIA GPUs. It also includes scripts for data processing and launching your own training runs. On their Hugging Face page, you'll find their 210 million and 610 million parameter models, plus code examples, to get you started with feature extraction right away. Alright, so this figure lays out their two main experiments. First is pre-training from scratch, starting with a random model. They use either causal language modeling, which is like predicting the next word, or masked language modeling, a fill-in-the-blanks task. The top plot shows that a hybrid approach, mixing both methods, gives the best accuracy, outperforming a pure masked language model run. Moving to the second experiment, continued pre-training. Here they take an existing model and train it more. And what they find is that taking a pre-trained causal language model and then applying masked language modeling to it provides a massive performance boost, far more than continuing to train a masked language model. This result really highlights their core finding about adapting existing models effectively. Building on that, these plots dig into the details of the masked language modeling method itself. The key question here is, how much of the text should you mask or blank out? These charts show performance across 4 task types, like classifying a sentence, answering a question, or retrieving information. The colored lines represent different model sizes. And what's really interesting is that there's no single best answer. For some tasks, more masking seems better, but for others, the optimal percentage changes with the model size. This complexity highlights that finding the perfect setup isn't straightforward. Okay, so with that complexity in mind, these bar charts give us a direct head-to-head comparison. We see masked language modeling in blue and causal language modeling in red across different model sizes. The charts cover 4 task types: sequence classification, or categorizing sentences; token classification, which labels individual words; question answering; and information retrieval. And for most tasks, the blue bars are clearly higher, showing masked language modeling is generally stronger. But notice the exception for token classification, where causal language modeling is actually competitive, and even wins at the 610 million parameter size. So given that causal language modeling is so efficient early on, these plots test a powerful idea. What if you combine it with masked language modeling? The horizontal axis shows what percentage of the total training is dedicated to causal language modeling first. And across all 4 tasks, you can see the performance peaks somewhere in the middle, not at 0% and not at 100%. This strongly suggests that a hybrid, 2-stage approach, starting with causal language modeling and then switching to masked language modeling, gives the best results. Now, to ensure all these comparisons are fair, it's crucial to have a controlled experimental setup. This table details exactly that, showing the architecture and training settings for the 3 model sizes tested. You can see the model scale from 210 million to 1 billion parameters. As they get bigger, things like the embedding dimension, which is the size of the numerical vector representing each word, also increase. The training section shows that many key settings, like the AtomW optimizer, the algorithm that updates the model, are kept the same. This careful control is what makes the conclusions so convincing. So wrapping it all up, this incredibly thorough study gives us a clear answer. While masked language modeling, where a model fills in blanks, generally leads to the best final performance, it's not the whole story. Causal language modeling, where a model just predicts the next word, is much more efficient and stable early in training. The key takeaway is that a hybrid approach, starting with causal language modeling and then switching, gives you the best of both worlds. That's all for this AI Research Roundup. Thanks for tuning in.